Hello, welcome to my video on data structures. In this video, we will discuss dynamic hash table and rehashing. In the previous video, we have discussed the basic idea of separate chaining. We know that we're trying to maintain the load factor of the hash table within a given range. If the load factor is too large, the sizes of the linked lists can be large, and the search and deletion operation can take a long time. On the other hand, if the load factor is too small, we are wasting too much memory. As a result, the size of the hash table should be dynamically adjusted according to the number of records that are currently stored. In this video, we will discuss issues relating to how to design such a dynamic hash table. Recall that our goal is to keep the load factor between 1/8 and 1/2. To ensure the target load factor range, we can adopt the following strategy. Specifically, when an insertion makes the load factor larger than 1/2, we will double the current size of the table. When a deletion makes the load factor smaller than 1/8, we will reduce the current hash table size to half. This is an illustration of table doubling. It is easy to see that after table doubling, the new load factor becomes 1/4. Similarly, after table halving, the new load factor will also become 1/4. As a result, the new load factor after table doubling or halving will be 1/4, which is within our target range of 1/8 to 1/2. It means that the hash table can take a number of insertions and deletions without needing another table doubling or halving. Denote the current hash table size as m. The hash table can accept at least m/4 insertions without doubling. Similarly, the table can also accept at least m/8 deletions without halving. As a result, we can see that table doubling and halving do not need to be performed frequently. We will come back to this conclusion later in this video. Now, let's see what other things we should do after table doubling or halving. It is tempting to simply call the reserve operation from the vector data structure to perform table doubling or halving. Recall that the reserve operation simply copies data from the old memory block to the new memory block. In our case, the reserve operation will copy the linked list addresses to the new location, but it will not change the linked lists. It does not alter the hash function and cannot evenly distribute the existing records across the entire range of the new hash table. As a result, it will not address the cluttering problem either. To address this issue, we need an additional step called the rehashing. The idea of rehashing is, since the hash table size is changed, we should also change the divisor of the modulo operation in the hash function. In this case, the records can possibly be distributed to any possible location of the new hash table. Since we have changed the hash function, we will recompute new hash values for all records and assign new locations for them. For example, consider the example shown here. We have 4 records with keys 4, 8, 12, and 16. The divisor of the modulo in the ohash function is 4, which is exactly the size of the ohash table. All records were stored in the first hash bucket of the ohash table. After doubling the size of the hash table to 8, we will update divisor in the hash function to 8, which matches the new hash table size. Then, we recompute the hash values for all records using the new hash function. We can see that record 8 and 16 are now stored in the first bucket of the new hash table, and 4 and 12 are stored in the fifth bucket. The largest size of the linked list in the new hash table is now reduced to 2, compared that of 4 in the old hash table. Although rehashing can reduce cluttering, it also involves additional computations as we recompute the hash values and redistribute the records. Since rehashing applies to every single record, it is easy to see that its time complexity is O(n), where n is the number of records. As a result, we need to revise the time complexity for the operations that might trigger rehashing. Specifically, for the insertion and deletion, their time complexity is increased to O(n) when they trigger table doubling or halving. At the first glance, the linear time complexity for individual insertion or deletion may seem daunting and make the large number of such operations invisible. However, as we have discussed earlier, table doubling and halving are not being performed very frequently. And only performing several times of them among a large number of insertions and deletions seem acceptable. As a result, we would like to know precisely the time we will spend for a large number of insertions and deletions. The idea is to even out the infrequent but heavy workload, such as table doubling and halving, among a large number of operations, and see how much effort should each operation undertake. This type of time complexity analysis, or amortized time analysis, is a powerful way to estimate expected time complexity in real cases. Let's consider the insertion operation, which may trigger table doubling. Recall that the initial load factor of the hash table is 1/4 after the previous size change. It means that we have n records and the table size is m equals to 4n. In this case, we will need to perform another n insertions before triggering the next table doubling. The first n-1 insertions will not trigger table doubling, and each of them can still be performed within O1 time. Therefore, their total time complexity becomes O1 times n-1, which is On. The last insertion triggers a table doubling. Since the hash table already contained n records before any insertion, it contains 2 n records after the n insertions. Therefore, we need to rehash 2 n records, and the time complexity for the last insertion is O2n. Then, we can compute the amortized time complexity by dividing the total amount of effort by the total number of operations. The orange terms in the formula correspond to the n-1 insertions that do not trigger table doubling, and the red terms correspond to the only insertion that does. The resulting amortized time complexity remains O1, a constant time. It means that if we perform a large number of insertions, we can expect each will still only take constant time, even accounting for the possibility of triggering table doubling. Now, we consider the deletion case. Again, assume that the hash table contains n records and has a size of m equals to 4n. In this case, it takes n/2 deletions to trigger a table halving. Since the hash table contains n records before its deletion, it now contains n/2 records. Rehashing is performed on these n/2 records, and it takes O n/2 time. The corresponding amortized time complexity is OL in this case, where L is the average linked list size in the hash table. Similarly, the conclusion is that the deletion operation time complexity is unchanged, even with the consideration of table halving. Our discussions above correspond to an extremely ideal scenario, as the hash table accepts a series of identical operations. However, we know that in real cases, the hash table is more likely to accept a series of random and interleaving insertions and deletions. Now, let's consider the case with a series of interleaving insertions and deletions. Note that allowing for both insertions and deletions will in fact delay the table doubling or halving, as they can cancel each other out. Consider a hash table that can accept 2 more insertions before doubling. If we allow for deletion, the hash table may accept 4 or even more operations before doubling. For example, insert, delete, insert, and insert. As a result, the frequency of table doubling and halving is reduced with the interleaving insertion-deletion case. And the amortized time complexity we have established before will still hold. Finally, I would like to add a note regarding the hash table size selection. Recall that in the previous video, we discussed why we should use prime numbers as hash table size. As a result, when performing table doubling with an existing size of m, the target table size will be the smallest prime that is larger than 2m. Similarly, when performing table halving, the target table size will be the smallest prime that is larger than m over 2. You can see that we accept a bit of space waste to ensure a constant time complexity of the operations. Also, note that directly calculating the smallest prime number that is larger than a specific value is difficult. Luckily, the set of prime numbers up to a given limit has been calculated and can be found from various sources. In this case, we can simply preload the set of prime numbers and look up the table when we need to perform table doubling or halving. In summary, we have discussed general idea of dynamic hash table. We have discussed the need for rehashing, and we have discussed strategies for table doubling and halving. Finally, we analyzed the amortized time complexity for insertion and deletion with the consideration of table doubling and halving. In the next video, we will discuss the implementation of hash table with separate chaining. Thanks for watching and see you next time.